This mini lecture is about applications of hybrid orbitals. As I alluded in the earlier hybrid orbital mini lecture, we talked about the different hybrid orbitals and how they had specific templates or shapes as far as the sp3 arrangements, sp2 arrangements, sp arrangements go. And what we found was that there were specific ways these orbitals were arranged and specific shapes. And we found this one to be tetrahedral, sp3, 109.5 degree bond angles. That's between these hybrid orbitals. We're going to have 120 degree bond angles for the sp2 and a shape called trigonal. And then a linear shape for the SPs with 180 degree bond angles. That's what you're going to see right there. Now also what we can do is we can look at an example. This is a similar example to what you might see on a test, where you can look at different atoms and figure out what the hybridization might be. Now you can do that by looking at the bond order for each of these. Now the single bonds will be sp3, the double bonds will be sp2, and the triple bonds will be sp. And this is all related to the number of objects that we're going to see attached to each of these atoms. Now if we take number 3 for example, number 3 is single bonded, but it actually has 4 things attached to it. We're going to have 2 hydrogens that aren't drawn in, but we've got 1, 2, 3, 4 things attached to atom 3. Now 4 things attached to atom 3 would be 4 objects. Now 4 objects, we need 4 hybrids because we've got 4 things that need to be bonded to that central atom. And that means we need 4 orbitals to make those hybrids. And that means that we're going to be sp3 hybridized on that particular hydrogen right there. That needs 4 orbitals, 1 s and 3 p's to make 4 sp3 hybrids. In the case of atom 1, you can see that there's going to be 2 objects attached to atom 1, and that means there's going to, 2 hydrogens, that means there's going to be 3 objects. Now 3 objects means 3 hybrids, so we're talking about an sp2 type hybrid right there. So number 1 is sp2, number 2 is sp2, number 3 is sp3, number 4, you've got a double bond here, so it's sp2, number 5 is a little tricky because there's a carbon here and a carbon here with a hydrogen on it, and that means that this oxygen is completely single bonded, so that's going to be sp3. And we can get that also by looking at the number of objects attached to the oxygen, 2 bonds and 2 sets of lone pairs for a total of 4, needing 4 hybrid orbitals. Over here you've got number 6, that's going to be sp hybridized because that's a triple bond. So in summary, what you can do is just look at the bond types. You can say single is going to be sp3, double is going to be sp2, and triple will be sp. Associated with each of these hybrids will be those shapes. For sp3, tetrahedral, 109.5 degrees, sp2, trigonal, 120 degrees, sp linear, 180 degrees. If you need more information about that, go back and take a look at the last mini lecture. Now related to this also will be the way that these hybrids join together. And what we're going to see for these different hybrids, for example with the sp3, sp2 and sp, is that there's a link between bond length and the hybrids that we're talking about. Now in the case of sp3, these are going to be 25% S and 75% P in each case. So they're going to be more like P than they are like S. What that means is that we're going to have longer and thinner orbitals for the sp3 and shorter and fatter orbitals on the sp2, and then very short and fat on the SP. So, just drawing a couple of pictures here. Oops. Right, this might be what an SP3 looks like. This could be an SP2. And this could be an SP. And what you're going to see is that the SP3 looks more like a P than it does an S because it's 75% P. This one's a bit shorter and fatter because there's less P, and this one has less P still, so it's even shorter and fatter. So of course what that means when we're talking about these bonds and joining the hybrids together is that the SP3s are going to have longer bond lengths, and the SP2s will have shorter, and the SP shorter still. Of course you can see these bond angles, and these are the same bond angles as we were talking about earlier. So what that means is if we were looking at another kind of problem, something like this one for example, I'm looking at D here, and you were being asked to circle the compound with the greater, stronger or higher amount, and the amount was referring to bond angle. What you would do is you'd look at the two compounds and you would figure out the hybridization that you were seeing in each of them. Now if you've got CH4, you've got CH4. CH4 is going to be like this. That means there's four things attached to it. It's all single bonded, so we're going to go for an sp3 hybridization. Now in the case of this one, we're looking at sp2 hybridization because it's all double bonded. Now we know that the bond angle there is going to be 109.5, and we know that this bond angle is going to be 120 degrees. So if you were being asked which one has the greater HCH bond angle, here you go HCH, HCH, then it would be the C2H4. That would be the one you'd circle. And the reasoning you would use is that sp3 is 109.5 and sp2 is 120 degrees. Now let's say we change this question and we talk about bond length now. And you're asked which one has the greater bond length. Again, the reasoning would be based on hybridization. sp3 has longer hybrids than sp2, so CH4 would have the greater bond length than the C2H4 would. And that would be the one you would circle. Now keep in mind for this question, I don't have to just ask greater, stronger or higher. I can also ask for lesser, weaker and smaller.